Share screen. Oh, Noah was just mentioning before class, but V got a job offer from FIS. Pretty high offer too. I was impressed. So now our biggest concern is how does she drive to Milwaukee? Because she doesn't do the interstate.
She should probably move there.
Or you could take Port all the way down.
Yeah. Or well, are they in person?
I think at least initially. I don't know the exact dealio. All right, am I sharing my screen?
Yes.
Okie dokie. Well, man, I know you see the screen there, but it's shared on Zoom.
Oh, I don't know.
Yeah.
Yes, we're good.
Said it with such confidence. He was like, okay. I thought in my head too.
All right, I don't believe anybody. Yeah, it's shared. Okay. All right, so let's start off by, I want to start walking through the Proc code. And then after we walk through it, I'll come back by and we'll deal with these couple of issues if we get that far today. I mean, I'm like 99.9% positive that the this create proc entry thing, I've done a little Googling here in the background, is it's just an old function name from the library, probably from 15 years ago, and they've updated the library. We'll go and look at the header file manual page, and it'll be an interesting fix, but it's not compiling currently, but that's okay. All right, so let's go here. And I think I have the current here, and I'll just give you the broken code for now if you want to follow along. I think I actually already have it up there, but so my repository up on GitHub, I think it already had the folder for Proc FS module. I've only made a couple of things that made it more broken. But you know, that was on purpose as an exercise for the reader here. But if you want to follow along with the code, it is already up there. But let's kind of dive into it. So remember last time we were talking about character drivers and kind of the global idea here. If we were going to pigeonhole the systems programming stuff into like one concept, it's inter-process communication. Or actually, maybe even let's go more generic, communication between technology things, I guess. Processes are a pretty common thing. We think about the world of computers now as software. Every piece of running software has a process associated with it. I think last time we were looking at a couple of commands, ps-ax, they'll give all the processes currently running on the machine. I think I showed top, right, which shows the current processes that are taking up the most CPU time. Top also is kind of another feature. I didn't really point out some of the stuff, but if you look up top on top, it shows you the number of users, because remember, Linux is a multi-user operating system. You know, even though we're all using it as single user operating systems, I would probably say I'm making up this number, but I wouldn't be surprised if this is pretty close. 75% of all the websites, web hosts in the world are probably running on top of Linux or some type of Unix. The other 30 are .NET based, Windows based. Maybe it's closer than that, but I would be shocked if Linux did not have a strong lead. And it's not something that Windows is terrible and Linux is amazing. It has more to do just the nature of Unix. Windows grew up as a single user operating system. And then they started introducing their server products to kind of push the envelope for you know, having multiple people within like a local area network all talking to a file server or something like that. So they evolved into that, where Unix started off as a server-based system. and then kind of evolved consumer-ish, user-ish friendly applications with X windows and stuff like that, that made it a little bit more convenient for an individual to use it as their daily workstation. So it's less about who's good and who's bad and more about just kind of their story. All right, so, you know, Linux is just gonna be the better operating system for multi-user because it's gone through the history of that. But they give us an idea for like the load average. You know, these numbers mean something related to like, this is time on the CPU. I think one of these is like user time, system time, and I don't know what the other one is. This is the difference between applications running as administrator versus normal plain Jane users. Number of tasks that are currently running, how many are running right now, number that are sleeping, CPU utilization. You know, you've heard me say before that something like 95% of the time your CPU is basically doing nothing. And you can see here that, you know, this is on a virtual machine, but, you know, it's less than 1% CPU utilization, so on and so forth. And the amount of memory being used. So it gives you some information about kind of current state of the machine. You can see the same kind of stuff with Windows. You can go into the system health report thing and it'll give you a nice GUI that kind of shows the same stuff. All right, let me kill this. So we're going into the proc file system thing and this guy right here. Okay, yeah, I mean, so rev the value. So we have some header file issues. So specifically the proc file system is to facilitate process communication, well, communication between processes running on the computer. And I think I pointed out last time, if we go into proc, if I do ls/proc, we see that we have a whole bunch of numbers in here. Each one of these is associated with one of those process IDs that we would have seen inside of top, or I think I ran the command last time, ps-ax, and this shows you all the processes that are running. If I wanted to like grep for code, why did that open that? Didn't I grep for it? Oh, no, I just piped it into code. So this will show me the things associated with VS Code, whatever. So things you can do in Unix. All right, so for right now, we're gonna assume that this is fine. We're bringing in libraries associated with the proc file system. We'll just have to fix whatever the current version of that is. The header file's probably changed a little bit. All right, so we're creating a something that's going to live inside of proc file system named hello world. All right, so again, going back out into here, when I did an ls on proc, notice that we have a bunch of these numbers. These are running processes on there. And then we have some other things that are just going to exist on here, and we'll kind of see how we stumble into that. We have the amounts directory, which is where like CD-ROMs are, USB sticks, stuff like that. All right, so we're going to define a variable that we're going to ultimately fill. This is going to be a proc directory entry. So there's going to be a struct of type proc directory entry that we're going to call our proc file, and we're going to fill it up with the information about that, and that's kind of below here. All right, so this guy talks about the different parameters that are coming in here, but we can probably read through it and see it. So when we read from a enunciate, when we read from a proc file, we're reading something. We saw this last time, kind of one of the go-to moves in Linux-based systems programming. Notice these things don't really return. Well, the value that's often returned is an int. What's that value used for? That int that gets returned by a lot of these functions? What are those values for? This kind of explains a little bit why I'm having to pass something like this in. So our functions in Linux, almost all of them, all these old school functions, they almost all return an integer. Now, an older language like C won't let you return more than one value. Objects didn't exist yet, so we can't return an object. You could return a struct, right? That would kind of let you pull off returning more than one value. But generally speaking, the return value we're using from these functions is for like error codes. Did it work? If it didn't, how didn't it work? Stuff like that, all right? So that's why almost all these guys, when we write them, they have a header type or a return type of int. Now, with that being said, one of the things when we read from a proc file, one of the things we want to do here is we want to get information from the file, which is a representative of a process. So remember, in POSIX-based operating systems, everything is a file. So even though everything inside of this directory here, this stuff like 2063, that is a file. But that file has like a direct pipeline to a running program on this computer. So when I read from this file, I'm really reading something from that program. And the program would have had to write to the proc file system in order for there to be something for me to read from. That makes sense? So the file is kind of our conduit. We don't want to think about these things as your standard text files that just have some stuff in them. They're kind of special. All right. So the idea here is if we're going to, this is a function we're writing here. If we're going to read something from the proc file system, then one of the things we're ultimately going to want from this is we're going to want the information that we read. We need access to the information that we read. And the way that we've seen this before with the character file system or the character device, is a common way this is done in C in general, but also systems programming in C on Linux, is you pass in a pointer to a string. So I'm saying, hey, here's some land where I will check this place after this function returns and look for the information you gave me. All right. So instead of you calling a function and receiving the string that it read as a return, the return value here is an integer. Did it work or did it not work? The value that we expect to get as a result is actually going to be stored inside of this variable here. It's called buffer. That's usually that naming convention, calling something buffer, typically should kind of clue us into it's that type of value. I'm giving you something that I expect for you to fill up. Just kind of something you'd see in a lot of these older system calls. All right, so I'm passing it a pointer to a string, and presumably inside of here, it's going to put the answer, whatever it read, inside that string. Okay. Char pointer buffer location. Well, it is a pointer to a pointer. So my char pointer to the buffer would be the base, the buffer where the data is to be inserted. And then the second thing is a pointer to, what is the second thing used for though? Buffer versus buffer location. Oh, okay. So really you have two, these are competitors. This first one is the kernel provides buffer space, lives in an administrative space in the kernel for you to store stuff. This is your standard go-to buffer, comes with the operating system. If you don't want to do that and you have your own string that you want it to load in, and it might not be a personal preference. It might be that maybe you have, if we kind of marry this to some other options for inter-process communication, maybe you have some shared memory somewhere. You've created shared memory or something else that is part of what's called IPC, inter-process communication. Whenever you see a capital IPC, so if you ever see something that says IPC like that, this stands for inter-process communication. These are the ways that processes can, let's call it tools, that processes can use to send/receive info from each other. An example of this would be something called shared memory. Think of shared memory as kind of like our singleton that we've looked at, like in Java, where we talk to the operating system. We say, look, I got a couple of programs here that want to send some stuff between each other. Can you reserve me a little, a bucket in memory that all of them will have access to if I kind of give them the code, the secret code. So it'll say, here's some shared memory. Here's memory that all processes will have access to. And assuming you have the identifier of that shared memory, every one of those processes, those programs can, with a couple of lines of code, effectively connect to that one centralized shared place and read and write stuff from there. Okay. You do though then have to kind of implement a cadence for, if I want process A to send information to process B, you need to kind of have a way of letting process B know that, oh, I've put something in our secret hiding place. So another way you might do that is through something called a signal. Okay, so we have, that's the observer design pattern. Okay, so the idea is that, you go and hide something and then you do your bird call or something like that, letting them know that, I put that stuff, in our secret hiding place, whatever. So you can use some of these different IPC approaches together. But it's no different than if you have a walkie-talkie and, there's that protocol, you say such and such and they say over, that means you're done. The other person's allowed to start talking, so you kind of create your little language and, we can invent that ourselves as we're deciding how we're going to use this shared memory. The shared memory is just a tool and both processes can read and write, can read from it, write to it, and then they can decide how do they control who gets to read, who gets to write, and how do they not overwrite each other's stuff. So IPC shared memory is an example. Signals, semaphores. Semaphores are a little bit more primitive. These are atomic integers that they increment and decrement atomically. So it's in exactly one CPU cycle. So it's less about directly communicating and more about controlling access to a resource. Think of it as kind of like a goalie, where, you don't get access to the goal, or only one goalie's maybe a bad example. It's like you have a cash register at McDonald's and 50 people are in line. They all are rushing to the cash register. Only one of them gets to order at a time. So somebody's going to grab that resource first. The semaphore locks it out. The semaphore is the bouncer that protects access to that resource. You don't get access unless you go through the semaphore. A couple of examples of inter-process communication. But these are things offered by the operating system as core tools to manage that communication. What we're looking at here is the support staff behind those tools for talking to multiple processes, finding processes that might be there. All right. So in any case, if we're reading from a file in the Proc file system, we'll give it the buffer location, how far into memory we need to walk to get there, how long the buffer is, where the end of the pointer to the end of the file, and then data. Let's see what they. Yeah, so all of these parameters may not get used, but data would be if you have a shared file that you're all reading from or something like that, you can say, hey, here's some stuff that your logic in here might work with. Okay, so inside here, we're gonna have our starting variable for whatever return type is. We'll print something to our logs. We'll say proc file read, whatever the name of the proc file is. If the offset is greater than 0, we've finished our read, I guess. I don't know, but it's just dumb logic, whatever. Just say if you're beyond the beginning of it, then do that. Otherwise, we're going to print to a string. We saw this before. So we're not outputting to the user, we're not outputting to the log. Instead, we're taking that buffer that was passed in. Okay, so even though we saw up above here that this parameter and this parameter can be used sort of interchangeably, depending on if the user wants to store something, the person who's writing this wants to store something in kernel space or wants to store it in wherever buffer location exists, which if the program is running in kernel space, it could be something else in kernel space, but probably it's something in user space. But the implementation in this example is assuming that we're writing into kernel space to this buffer. So in this else here, we're saying, look, we're going to print to a string. That's what sprintf does. What's the string? It's buffer. What are we printing to the string? We're just loading it with hello world with a \n. We're loading buffer with hello world. That's the end result of that guy. Okay, but we use sprintf. Well, actually, why do we use sprintf? Why don't we just say this? Why don't we say buffer is equal to hello world like this? What do you think? We're pretty used to working with strings. Go ahead.
Memory allocation?
Okay, tell me more. We're not, I don't know if you're right yet.
Because, well, I mean, just based off of the comments, it says fill the buffer, then return the buffer size. So I'm guessing that there's a certain amount of space there that we have to try to fit in.
Yeah, but the buffer size in this case would be the number of bytes that we wrote to it. So, I mean, we could do something like, I'll just hard code it to fake it. What's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is a character, so it'd be 12. Technically, it's 13. So we could say something like that because there's a \0. So I could replace this one line with these two lines. Because ultimately, the number of characters that I'm writing to this string will be 13. Why do I need to know the number of bytes written? Why is that useful information? Kind of goes back to how old C is. We're used to these modern languages where strings they can report their own length. When you load something into it, it just kind of works. Go ahead.
So then when you go to read it, you'll still have that information, so then you know, so you're not overstepping your bounds.
Yeah, so let's say that buffer, we'll just make something up. Let's say that the kernel defined that buffer as being 1,000 bytes, capable of holding 1,000 bytes. But if I'm putting hello world in there, I'm wasting a bunch of those bytes, right? I'm only loading the very beginning of that guy up. We own all that memory. Now let's say before when we wrote to it, we actually wrote 500 bytes. Now we're writing 13, but we wrote 500 before. Well, if we didn't know when to stop, what we do is as we start walking through it, using it in some other part of the program, we be getting our 13 new bytes written, right? The hello world part. Then we start stumbling into whatever started at byte 14 in the previous time that this was used when it wrote 500 bytes. Now, then once you get to the end of 500 bytes, you still have another 500 bytes of, this is presuming when we defined buffer, it was capable of holding 1,000 bytes. We allocated enough memory to hold 1,000 bytes. So now once you get to byte 501 to byte 1,000, I mean, you're just in random land, whatever the default value was for that byte of memory. Maybe the operating system was polite enough to put zeros in memory or something like that to just say, hey, you know, this is, you know, we cleaned it up for you. When we handed you this plot of land, we went ahead and, you know, we mowed the grass and all that stuff, you know, we cleaned it up for you. But there's no guarantee. You go to older operating systems where you had more limited system resources, processors were a lot slower. They might have said, look, we don't have time for that. Who cares if we leave a mess in memory? This is the memory you have access to. Deal with it. When you get there, If the picnic area is already mowed and you want to deal with this other place over here, go clean it up. We're not going to do anything for you. So there's a real possibility that, especially when we're writing to the same buffer space over and over and over again with different length values, that we might get to a place in memory that has an old piece of data that we wrote, or an old piece of data that we maybe didn't have anything to do with. Because the operating system has a memory manager that hands out memory addresses. All right, so if I say, hey, I need, let's say I'm a program that ran 4 hours ago, and it just happened to give me this memory space, memory address 100. Okay, so it gave me 1,000 bytes at memory address 100. My program ran, it did its thing, and then it finished. So I gave back, and let's say I was a good program writer. I deleted the memory when I was done, so I let the operating system know, like, hey, I'm done. You can hand this plot of land off to somebody else. No problem. The operating system goes in and it marks it off and says, oh, that we can hand this out to somebody else now. They're no longer using this land. Okay? But the state of the land is whatever it was left at. Memory is just a big old array, digital array. So if that guy wrote hello world back to back to back 1,000 times, or filling up 1,000 bytes in that space, and then gives it back hello world all those times, it's still written in memory. Just nobody currently owns that memory. So if you then hand it to somebody else, you say, oh, okay, you need a plot of land, no problem. This isn't used. You hand somebody else that memory. If they do nothing else and they just start walking through memory, printing out what they have, they might start getting some hello worlds out of that. It was still there. Nobody emptied it in an older operating system. They didn't clean up the yard. If you want data to be there, put it there. Don't assume the stuff you want is already there. And this is where you get into some of these, a lot of viruses are written with this in mind. Kind of some programs load things. It's the way they deal with some inter-process communication is by putting something in very specific places in memory. We see this a lot with video games. So the bots that run some video games, they operate under the knowledge of exactly where certain pieces of information are stored in memory. Okay, so let's say that you're playing a game and your current guy's health or something like that is stored in a very specific memory location. And you have this bot program that goes in and goes to that memory location and sets it to size of int. So now it's 2.1 billion is your guy's health. You're effectively immortal now in the game, right? You didn't go through the game to get the help, to get that health through a buff or something like that in the game. Instead, you went and had a third-party program change memory after the program wrote it there. Because from that point forward, that game is going to read from that place in memory to find out what's your current health. It's just a variable, right? You have a variable in that program that's called my health, and that value is stored somewhere in memory. Well, if you can find a way to go overwrite that part of memory, you got a whole new health, right? So how do these programs? I mean, a good example would be a lot of these different games have various bots in it. World of Warcraft is a game that's been botted a lot. Millions and millions of dollars of lawsuits and things like that associated with it. So the people who, like, one of the big bots was something called WoW Glider, was one of the early bots for it. And every single time World of Warcraft would release an update to the software, you would have to wait for a new. There was another one called WoW Buddy. That was actually probably the better example. Every single time that they released a new update to the game, you had to wait for WoW Buddy to come up with a release themselves, because they had to go through and update the memory locations of things. Because now you're talking about kind of a cybersecurity type situation. What did Blizzard Activision do? Whenever they made an update, they tried to shuffle those memory addresses around to break bots so they stop working. So now you're the bot maker. You now need to go and find out where the memory Health used to be stored here, now it's stored over here, for example. So if you're that bot writer, how do you go figure out where they put it now? If you're writing that, how do you figure out where the variable for health is stored inside of the computer? Okay, tell me more. I mean, terminal commands, sorting through.
You just use the terminal and eventually you probably stumble onto it. It's more of a brute force approach. But...
Okay, well, you probably wouldn't use the terminal. You'd probably write a program.
Yeah.
And you'd say, okay, video games are probably living in user space, right? So you'll start a pointer. I mean, let's just take your brute force approach. They probably have some techniques where maybe they can kind of narrow it down a little bit to maybe a neighborhood. You know, if we think about this in real life, maybe we're, you know, we have a warrant for somebody's arrest and they're somewhere in the country, right? So now what do? You got to go and check every place in the entire country to go find the person. But if you can narrow it down to Mequon, right? I'm looking at you, Noah. That's not where you are right now. All right, so if you can narrow it down to a certain place in memory, you might have a better chance of finding it. But even if you narrowed it down to Mequon, that's not an instant find, right? You got to still wander around until you find the person. So if we just go brute force, what do? You create a pointer, set it at the very beginning of user space, and then start walking, bucket to bucket to bucket to bucket. Now, the thing is, you're going to find numbers in a whole lot of those buckets. So how do you know when you start getting into the numbers that you're looking for? Well, so now you're probably looking for certain strings or something that you happen to know are part of the game. You know, like World of Warcraft, one of the factions is called the Horde. So maybe you start looking for an H followed by an O, followed by an R, followed by a D, followed by an E. And at that point, you know you're in the right neighborhood. Then you take a bigger view of memory, right? And then you start thinking, okay, well, what kind of looks like it's probably the health? Something like that. You might even run the game and then go and investigate memory and you see, oh, my health is currently 1300. There's a 1300 right now. Maybe these are related. Something like that. So it's a tedious job, but you're literally walking memory, and a language like C and C++ allow you to do that. Languages like Java don't have a syntax for it, and memory is abstracted through a virtual machine in Java. So you're kind of getting an idea behind the scenes of how these things work, right? That doesn't mean it's easy because, you know, Blizzard Activision has probably some pretty smart people working for them. So they're doing quite a bit of things to try to be a moving target. They're also, at least on Windows, they have a program called Warden. And that program tries to detect when third-party applications are trying to inject information into their memory space. So you kind of have this thing that's kind of patrolling like a police car, patrolling memory, and it's looking like wait a minute, that is not what it should be. It's been changed. And then at that point, they don't even care why it was changed. They just ban you. I have screenshots.
So how did you do that check though? Like with the health example, would it just say like that number is way too big to be anybody's health?
Well, maybe. I mean, I'd be making it up if I told you what their actual strategy is, but it might not be that. It might be something, you know, they might just be looking for evidence of somebody messing with the memory. So maybe they might even put like an Easter egg somewhere in memory, or maybe they have something that is information that is in security. If you have the security classes, these are called honeypots. So you might put something in memory to attract them to it. Like, oh, that seems so obvious. You know, like health equals. Maybe not quite that obvious, but you know, they want you to do something with that because that then lets them know that you should be banned. You know, something like that. I'm probably oversimplifying it a little bit because now it's become, I mean, you imagine it's a big business now. You know, Blizzard Activision pays millions of dollars a year, I'm sure, to developers whose one job is to reduce the hackability of the game. And it's a constant job. Every single time they make an update to the software, they have to kind of rearrange their approach because they know the enemy out there, the people who are writing the bots, writing the viruses, whatever. And you can take this away from video games and put it on Windows, right? And say this is for an operating system type thing. You have the enemy out there who's looking for vulnerabilities. And sometimes the enemies aren't even the real enemies. Like the penetration testing class, you're basically doing what's called white hat hacking. You're saying, look, I know how the enemy operates. I'm going to say, let's see what I can do about the current state of this operating system. And then I'm going to report it back and let you know that you have a problem. As opposed to, I found a hole. I'm not going to report it to anybody. Instead, I'm going to delete your entire operating system. something like that. All right. But the overarching thing for us in here should be this idea of, memory is dangerous. And that's why we have the starting point in a modern operating system where we've separated kernel space from user space. Because those are kind of sacred places. Well, kernel space is sacred. User space, hey, if your program crashes, it crashes. They're separated so that user programs probably can't hurt the operating system. And now our modern day approach even takes it another layer. Now we actually run a lot of applications inside of some kind of virtual container. Might be a virtual machine if it's a Java-based thing, but at the very least, they run it in like a sub-environment where things are mapped to real memory. So you might have a program that has a pointer to a place in memory, but that is actually a pointer to a place in real memory. Well, it's a pointer to a place in fake memory, which then points to a place in real memory. So they abstract it to make these things further separated. So when they die themselves. And that was a big deal on Android devices. Less so now. I mean, what's kind of funny is Android should have not had this problem because it being based on Java, things are running in virtual machines anyways. But the early Android operating system would allow stuff to run. All the programs were swimming in the same user space swimming pool. So if one started going off the rails, it could potentially break other ones. And then you start using up all the system memory and things like that. And then your operating system becomes unstable, things like that. Well, now each application runs in its own little virtual pod. So you typically would have an application crash, but it wouldn't really impact the rest of your phone. The things you start noticing that impact the rest of your phone are when things get into like loops. Best way of, the cheesiest way that happens is like on a website that has like JavaScript that just has an infinite loop and you just can't even get out of the page because it's using all the processing power running the JavaScript. You're trying to hit the back button to get to the home screen. Once you're there, you can kill the app and you're fine. You can't get there because it's using up so much of the CPU time that the sub process that's keeping track of where you're touching on the screen isn't getting enough CPU time to listen. Make sense? I don't know. Interesting stuff. So all that was very related. That wasn't off topic. It was just a deep dive into what's going on here. So the idea here is that by doing something like this, historically, that might not have been allowed because string literals worked very weirdly. Now this is probably going to be allowed, but what you've lost out on is the control over what is the proper way to write a string to memory. So I'm saying that today you can kind of get away with it because C has been updated over the years to allow people who maybe are a little bit more cavalier with the way they use strings. But the right way to use strings historically, under the hood, a string has a base address and you have a bunch of characters and it's terminated with a \0. Okay, that's how strings are built. This power tool here, sprintf, says, look, you give me the thing you want to write to memory as a string, I'll write it the right way. That's what sprintf does. It puts it in memory the right way, even if we maybe would have gotten away with that.
So does it automatically delete or free up all the other memory? then?
No, because I mean, buffer, I mean, you're at the mercy of whatever buffer is. In fact, actually, from a C perspective, since char pointers, they don't know about their size. So frankly, let's say buffer is only 3 bytes. Nothing keeps us from doing this. Right there, that's all I was allowed to put in memory. That's all I was supposed to put in memory. You know, it's kind of like maybe I used the example in a previous class where you buy a house and you start building crap in your neighbor's backyard. C will let you do that. Like, look, just because I asked for memory doesn't mean I have to stay in my own swimming pool. I can go over to the neighbor all day long. Yeah, so, you know, Noah's question was, well, since if we assume the other extreme, let's say buffer can hold 1,000 bytes, and I only put 13 bytes in there, will it then free up the rest? No. All it's done is it's made sure to put the proper termination character in there. In fact, it didn't even clean up the rest of those 1,000 bytes in there. It just made sure that if you're going to go and print or something from the string, which automatically looks for the first termination character, it'll find that termination character at bucket 12, not at bucket 999. There might be 20 other termination characters along the way after there, but it terminates at the first one it bumps into. Okay, so this power tool is write this thing to this place in the correct way for writing strings. Make sense? All right, so even if we could get away with that, it wouldn't be the proper way of writing it. All right, so then in the end, we're going to go ahead and return the number of bytes that we read, because whoever called upon this, which is going to be the Proc file system tools, he's going to be interested in the number of things that were read from this, because sometimes all the reading doesn't take place in a single read. Today they're done with P streams, well, P threads that use streams. So you might, to get 1,000 bytes, you might read 200 bytes, then you might read 300 bytes, and I just recognize what I said. Oh, I hate you people. That was just making me like trying not to laugh. Oh. I'm glad the weekend's here. Okay, so in any case, this would be the function that will get called. We still have to register it with the proc file system, which is going to come later, later down here. All right, now we start getting into places that we're used to. Here's our normal module code at the bottom here. We're going to see actually, we don't see it in here where we install the module. We associate it, but whatever. The init module, this is the function that we would use the module API to say, here's a module to go ahead and associate with the system, and it needs to follow this, this cadence. This is where I started having some errors, because I think this proc entry, so we're adding, we named our thing, have a hello world up here or something like that. We wanted our proc file system name to be hello world. That's what the file is going to have named inside of /proc. So there's a function that belongs to procfs.h that creates a proc entry. Now, if I do let me just look something I have to real quick. What's the name of that? procfs.h underscore. Proc underscore fs.h. I was just seeing if it had the method headers in here real quick. Yeah, it doesn't, not a big deal. So I'll have it fixed before next class. But the idea here is that there is a function that will create an entry in the proc file system. And it's probably called something pretty close to that. Maybe it's called create proc or proc create something like that, but it'll be something that whose job it is to create this file inside of the proc file system. And these are the default permissions for it, 644. So 644 is read write by the owner. 44 is read only by the user, and it's read write by the owner, read only by the group, read only by everybody else. So that's associated with like chmod 644 to change the mode of a file. Okay, so we'll stop there. I think we should be seeing this starting to look fairly similar, the stuff that we're creating. I'll figure out the deal with the proc file system for Monday. I won't give it to you to fix over the weekend. So no homework for Monday, but I will see everybody then. And assuming we have this working, we'll probably have an assignment on Monday, due Wednesday. Questions, comments, concerns, bribes? All right, I'll see everybody on Monday.